Good evening, everyone. We have a presentation today from our friends from UCLA and Cruise Automation entitled Learning-Based Expression and Head Pose Transfer from Images and Videos. But before that, let me tell you about our chapter. So the Silicon Valley chapter of ACM SIGGRAPH has been existing for more than 14 years. And you see some of the officers here, Carl and Aleph, who had been previous chairs of this organization. We try to have activities and events monthly. Like for this year, for the year 2021 and 2022, we had events every month, and they range both from local events and even international speakers. This year is also memorable for us because it's the first time that our chapter has been featured in the ACM newsletter March issue. So hopefully you can look into that. But let's get into our presentation now. First of all, thank you so much, Xiao and Surya, for presenting. Again, I'm your chair, Elisa, here. Just to let you know that the face and head movements are a powerful mode of nonverbal communication among humans. Endowing anthropomorphic characters with the ability to produce such actions autonomously is crucial for making digital twins of themselves. Xiao and Surya will also introduce a deep neural network-based method for learning the representation of expressions through Ekman's facial action coding system, FACS, in the context of a muscle actuators that drive musculoskeletal face model augmented with the neck-head system to animate head movement during facial expression synthesis. This presentation will basically, in summary, be a learning-based approach to transfer facial expressions and head poses from images and videos to a biomechanical, muscle-driven face, head, neck complex. Now, introducing our speakers here, we have Xiao Zeng. She's an Master of Science graduate in computer science at the University of California, Los Angeles. He's continuing his PhD research focusing around facial expression and head pose transfer from videos and the simulation of musculoskeletal human model and artificial life. Also, a UCLA graduate in Masters in Computer Science, we have Surya Dwarakanath. Surya's research interests spanned artificial life, computer graphics, and deep learning. As a software engineer in simulation at Cruise Automation, Surya's work involves the use of machine learning and simulations to improve technology for self-driving cars. Go ahead, Xiao. Surya.
Okay, yeah, thank you so much, Elisa. So today, together with my colleague Surya, we want to talk about our work in learning-based expression and head pose transfer from images and videos. Especially, we want to introduce an integration of this transfer pipeline and a biomechanical face head neck complex as shown on, in the images on the right. This talk is based on our poster presentation in ACM SIGGRAPH SCA 2021, and also our paper in International Symposium on Visual Computing last year. So before we dive into the details of our model, let us to introduce ourselves a little bit. So as Elisa mentioned, I'm a PhD student at UCLA, and I'm a member of the Computer Graphics and Vision Lab, led by Professor Dimitri Tzeplis. There are two major branches of my current research. The first one is the development of muscle-driven biomechanical human animation system and the neuromuscular controller. So there are two projects under this branch. The first one, in the first project, we aim to build this face head neck complex with its neuromuscular controller, which is the focus of our talk today. In the second project, we are trying to build a hand forearm model as well as the controlling part. And the second part of the second branch of my current research is the simulation of artificial life. Specifically, I'm trying to develop a behavior model for a large group of schooling fish to generate a realistic synthetic data set for various underwater perception systems. And I will let Surya to introduce himself.
So right now, I'm a software engineer at Cruise Automation, and my current work at Cruise involves generating some kind of synthetic data to train ML models for autonomous vehicles. And as a graduate student, I was also a part of the UCLA Computer Graphics and Vision Lab under Professor Dimitri Tosopoulos. And my research at UCLA spanned the use of deep learning for expression and pose transfer for the biomechanical head specifically. So that's a bit about me, and I'll pass it back to Xiao for the presentation. Yeah, thanks.
Thanks. Yeah, so this outline for our talk today. First of all, I will introduce the motivation and objectives behind our research, followed by some related works that's directly relevant to our project. Then I will give an overview of the framework, as well as talking about the musculoskeletal model that we used in this project. So there are two parts for the musculoskeletal model. The first one is a head-neck system, and the second one is a biomechanical face simulator. Then Surya will talk about the controller part for this framework, which consists of the open face toolkit and offline learning module and online transfer module. And then Surya will also introduce the result of our framework. In the end, I will give a summary of the talk and discuss some future extension of this project. Okay, so as we all know, in recent couple of years, the terms like metaverse and digital twins have become increasingly popular. Everyone is expecting to interact with realistic human-like characters in a virtual world as part of our daily life in the near future. The realism of the animated human behavior and characters has been improved to a level that is nearly indistinguishable from those of real human. However, such realism is often achieved by some kind of manual tuning process. As shown in the left figure here, the facial rigging of a human character based on the facial action coding system, or FACS, requires artists to manually set the deformation of face mesh in keyframes. And in the grasping animation on the right side, the hand is driven by the skeleton information, such as the joint angle that's recorded in the motion capture data. This dependency on manual intervention is even more severe for muscle-driven human models, which differ from conventional skeletal models and capture the anatomy and physics underlying human motion generation. These kinds of models often more complex than the conventional skeletal model by its nature. In this work, we want to endow muscle-driven human-like characters with the ability to perform interactive actions, especially through facial expressions and head poses in an autonomous manner. We choose these two types of actions because they are the most powerful modes humans use to communicate thinking and feeling in a nonverbal way. We would like to use a learning-based approach to achieve this goal. For the biomechanical face head neck model shown below, a natural approach is just letting the model to learn from human images. Or in other words, we transfer the expressions and head orientations from human images onto the model. So before we introducing the details of this model, let me first briefly discuss into some previous work. So some of the existing biomechanical face models are already capable of generating facial expressions, like the one developed by Tsiopoulos and Lee in 2004. But it requires manual setting of muscle weight to activate each facial muscle, as well as extensive parameter tuning. Wu et al. Developed a face model that uses finite element volume mesh to represent tissue layers and muscles. It can simulate a wide range of expressions. However, it cannot run in real time, which is one of our sub-goals. For the head neck system, Lee and Tsiopoulos have also developed a model with heel-type muscles and a neuromuscular control. We actually used it as the basis of the head pose animation in our work. And speaking of the domain of expression transfer, Zafakis et al. proposed a solution to automatically determine the muscle activation for anatomical face model using motion capture data. Some of the other works, such as the one by Weiss et al. And Zhang et al., focus on the real-time expression transfer onto blend shapes, but they lack the anatomical details that a muscle-driven model provides. And in our work, instead of using the motion capture data, which can be difficult and also expensive to collect, we choose to leverage the facial action coding system, or FACS, as an intermediate representation of the expression space of our model to learn from. The FACS was firstly proposed by Ekman in 2002. It's a well-known scheme to decompose facial expressions into the intensity levels of action units, or AUs. Each AU corresponds to the action of one or more facial muscles. So by doing this, it encodes the anatomical semantics in an abstract way. Of course, these related works are far from extensive. We only introduce the most relevant ones to this project. Okay, so given the background of the muscle-driven facial animation, what we built is a novel machine learning framework to transfer facial expressions and head movements from images and videos to a biomechanical face, head, neck model. So our framework has three major components. The first one here is the one in the green box, is a musculoskeletal head neck system. The second one, the one in the red box, is about mechanical face simulator. And the third one in the blue box is a facial expression and head pose control. So let me first introduce the head neck system. So the head neck system is an anatomically consistent model that controls the head pose. It consists of a voluntary controller with this blue outline that receives the current head neck pose and the velocity information, as well as the desired adjustment. It generates the muscle activation and the set point signal and pass them to the reflex controller. The set point signal contains the desired muscle string and string rates. Then the reflex controller with this yellow outline adjusts the muscle activation according to the set point signal and the current string and string rate, then pass the muscle activation to the neck muscles. The muscles with this brown outline, they are implemented by heel type model, which I will introduce very soon. It receives activation and output contractile force to pull the neck bones. By doing this, the model completes the head movement. The entire system has 3 rotational degrees of freedom, which are pitch, roll, and yaw. It's capable of making most of the common head movement with a combination of the 3 DOFs. So here are some more details about the neck model. So there are a total number of 8 joints in the cervical columns. The red points on the right side represent the pivots of each of the 8 joints. And the C1 and C7 are just the labels for the cervical bones. There are a total number of 72 muscles, and each of them can span multiple bones. The muscles are arranged in 3 layers. The red ones are the deep muscles, the green ones are the intermediate muscles, and the blue ones are the superficial muscles. All of them are built based on human anatomy. This layer structure not only guarantees the controllability, but also allows greater flexibility for the neck movement. Also note that although 72 muscles seems a lot, but actually we omitted some of the muscles, such as the hyoid bone that's beneath the tongue, just for model simplicity. And the muscle force is computed using a modified version of the heel type muscle model. The total muscle force, Fm, is the sum of Fp and Fc. The Fp is a passive restoring force due to the muscle elasticity is controlled by the stiffness and damping coefficients, as well as the strain and strain rate of the muscle. The FC is a proactive contractile force, is proportional to the activation level, which has a value between 0 and 1. The muscle's activation, it controls the net force generated by each muscle. Each muscle has a linear activation level, where 0 indicates no activation and 1 is full activation. These activation levels are the output of a neural network that is trained based on the synthesized dataset generated by the neck model itself. And more details of this can be found in this and Terzebel's work. This FC, the contractile force, is also influenced by the force length relation and the force velocity relation of the muscle model, which are depicted in the figures below. The force length relation represents the muscle force as a function of its length. The LM in this case is the minimum length, muscle length that can produce force, and the L0 is just the resting length of the muscle. The FC, the force velocity relation represents the muscle force as a function of its shortening velocity. The VM in this case is the maximum contraction velocity under no load. So the second part is the biomechanical phase simulator. Is another muscle-driven model that we significantly improved upon the work of Li and Terzebel. Compared with their work, we increased the number of facial nodes that muscle force can be applied on to give the model more details, such as the wrinkles. And we also added the automatic control part, which takes in desired muscle activation to generate corresponding expressions. This model is physics-based. It can run in real time. And it also has a layer structure with 3 major components, which are soft tissue layer, muscle layer, and the scalp. So the soft tissue layer is a model as a lattice of uniaxial viscoelastic units. They are arranged in a multi-layered prismatic structure containing the fascia, dermal fatty, and epidermal sublayers. And beneath the soft tissue is the muscle layer. So there are 26 pairs of muscles, which are illustrated as the red-blue vectors in the figure on the right. One end of the muscle vector is attached to the bone, and the other end connects the soft tissue layer. So the contraction of these muscles basically applies force to the soft tissue layers and generates deformation to produce meaningful expressions. The innermost part is just the scalp that supports everything. So this model is capable of synthesizing 6 basic expressions and their combinations. The 6 expressions are joy, anger, surprise, sadness, disgust, and fear. So in this slide, I will show a demo of the face, head, neck system. I will start with showing the movement of the head, neck system. So in this part, we define a point in the 3D space with the changing coordinates, and we make the head facing towards the point. And you can see as the head, as the face looking upwards, the movement of the neck looks pretty natural. In the second part, we show different layers of the face, biomechanical face, as well as the expressions. This is the muscle layer. This is the fascia layer, and you can see the lattice structure. This is the dermal fat layer. Okay, so now I will pass the present to Surya, and he will talk about the controller part as well as the result.
Yeah, thank you, Xia. So to break down the control part of this expression transfer and post-transfer pipeline, I'd like to break it down into 3 parts. So the first part would consist of a third-party software called OpenFace. The second one is our offline learning module, and the third one is our online transfer module. And I'd also like to focus on some of the features of this particular control pipeline. So This particular control pipeline based on deep learning is trained offline using the synthetic dataset generated by the biomechanical phase model itself. So at least for the training part, we are not dependent on any third-party dataset or any dataset available outside online. And the expression and head pose controller takes an image as input and produces muscle activation and jaw rotation as output. So to give an overview, when a human smiles or a human makes a sad face, they produce some kind of expression that is taken as input for the controller, and the controller gives an output of muscle activations for the muscle driven model, which then produces expressions in the biomechanical phase. Next slide, please. Yeah, so talking about the open phase part of this control pipeline, I need to first outline that we take the biomechanical model. We have certain synthetic weights or labels based on visual analysis, and using those particular labels, we assign some muscle and jaw activations to produce some expressions in the biomechanical model. Now, given these muscle activations and given the expression that the biomechanical model produces, we pass it to open phase to get some action units. And these muscle activations which we provided and the action units which we get out from open phase will be the input and output for the deep learning based algorithm, which we'll be using further. And in the next slide, I'll be explaining a bit about OpenPhase, the software which we use to get the action units based on some expressions. So OpenPhase is a toolkit which, given an image of the face, is capable of getting fax activations, which is a fax-based action unit estimation, which signifies the presence and intensity of a particular expression. So I can give you a very small example. Our smile is denoted by action unit number 12. So if we have a very slight smile, we would have an AU12 of about 1.0. But if we have a very wide smile, it might increase to about 2.5 or some value from 1 to 5. OpenPhase is also capable of facial landmark tracking. So if you can see the particular image here, you can see dots across his eyebrows, his eyes, his mouth, and his nose. So these are important points in the face which can give an idea of how the face is positioned and what are the position of the lips, so that all the action unit estimation can be done. OpenPhase can also do eye gaze estimation. So it can generate a vector for the direction the eyes are looking at. And it also gives head orientation estimation in terms of pitch, roll, and yaw. So OpenPhase in the background is also built upon deep learning, is built upon deep neural networks. And it detects the action units or detects the intensity of action units using a linear kernel support vector machine. Next slide, please. Yeah. So coming to the offline learning module. So as I had mentioned before, our control pipeline is trained on the data generated from our biomechanical model itself. And this is the part which exactly deals with that. So training data generated by random expressions created by some variation of muscle activations is used as input for this learning module. So as I had mentioned before, we pass muscle activations based on some predetermined visual analysis to the biomechanical model. This produces some expressions in the biomechanical model, which is then passed into OpenPhase. And we get these action unit intensities from OpenPhase. So right now we have two different two different sets, the muscle activations and the action units. And the deep learning network takes these action units as input and outputs muscle activations as outputs the muscle activations. So our training process involves learning a pattern, learning a mapping of action units to muscle activations. So yeah, and to summarize that point, the network is trained on training pairs, which consists of action units as input and muscle activations as output. So this pipeline here outlines it pretty well. The synthetic muscle weights for 6 expressions gives rise to expressions, which is then passed to open phase to get action unit intensity. And the muscle activations from the synthetic muscle weights and the action units are used to train the expression learning neural network. In the next slide, I will be explaining the online transfer module. So once the offline learning module is trained, we can go ahead and use the online transfer module whenever we need it. So once a neural network is trained, it is capable of transferring the AU values, the action unit intensities, received by open phase into muscle activations. So in this particular part, we take a real human facial image or video. Since we have the facial image and even videos can be converted into individual image frames, we pass all of that to open phase to get action unit intensity. Now we have the offline learning module, which is a trained expression learning neural network. We pass these action unit intensities into that neural network to get our desired face muscle activations. So these desired face muscle activations and the head orientation measurements, which is reported by OpenFace, is passed to the biomechanical model to reproduce the expression the human is making in the image or in the video. And the major advantage of this online transfer module is that it is completely independent of the offline learning module. So once the offline learning module is trained, we can go ahead and use this as many times as we want. And it is also much faster because the training is already completely done. In the next slide, I'll be discussing some neural network architecture. So we use a neural network with 4 hidden layers and 100 nodes each. So this architecture was decided after comparing the mean squared error of networks with different number of layers. And first of all, I choose to use a normal artificial neural network because we deal with only numbers on both sides. We deal with action unit intensities, which is a set of numbers, and muscle activations, which is again a set of numbers on the input and output side. And hence a simple artificial neural network serves this purpose the best. And again, the architecture was decided after comparing the MSE of network with different number of layers. So we tried an artificial neural network with 3, 4, 5, and up to 10 layers. And we found that an ANN with 4 layers produced the best output. So the input dimensions are equal to the number of AUs output by open phase. And if I'm not wrong, open phase outputs 17 AUs of relevance to us. The output dimensions are the number of muscle activations and jaw activations combined, which I think amounts to about 56 outputs totally, with 52 being related to the expressions and 4 being related to jaw activations. So in the next slide, I will be explaining about the transfer result on the KDEF dataset. So just to outline the KDEF dataset a bit, the KDEF dataset has multiple human subjects enacting all 6, in fact, 7 different expressions. So which is fear, anger, disgust, joy, sadness, surprise, and a neutral expression. So since we focus on the 6 major expressions here, I will only be discussing fear, anger, disgust, joy, sadness, and surprise. So as you can see from this result, the biomechanical model is capable of producing or reproducing the expression made by the human in all cases. There is a clear-cut difference between the different expressions, and it also looks realistic to the people observing it. Next slide, please. So here we also present the transfer result with orientation. So even when orientation is included, the expression is maintained. So as you can see from the left image, the expression of joy is reproduced, and the orientation, the person looking towards the right, is also captured by the biomechanical face. And again, on the right side, the expression of disgust and the human looking towards the left is captured by the biomechanical face. Next. Yeah. We also have a video of the transfer result, which we will showcase right now. Yeah. So even though videos are a set of frames and each frame is passed individually to OpenFace to get the muscle activations for that particular frame, the video transfer result signifies that the biomechanical face is very sensitive to the action unit input, and that the difference in each particular frame can be identified by the biomechanical model. So each subtle expression the human makes or the human changes is actually reflected in the muscle activations and hence reflected in the expression of the biomechanical model. Even subtle movements like the eyebrow movement, the very subtle lip movement are captured by the biomechanical face, which makes this control pipeline pretty, which results in a lot of applications for this particular control pipeline. So I will pass it back to Xiao for the summary and the future work.
Okay. Yeah, so as a summary, we present the first biomechanical face, hand, neck animation system that is capable of learning to reproduce expressions and head orientations through neuromuscular control. This controller learns to map between the FACS action units extracted from human facial images / videos and the activation of the muscle actuators that drive the biomechanical system. And our approach does not require any manual data collection. And as the training data is generated directly using the biomechanical model itself, as Surya mentioned earlier. And this only needs to take place once in advance. Once trained offline using the synthesized training data, the neural network can quickly transfer a large number of facial expressions based on the reference images. So unlike some popular face tracking softwares, which requires many calibration steps to transfer expressions of different subjects, our approach needs no additional parameter adjustment to perform the same task. Of course, we will need to obtain the facial texture and mesh for each subject to further augment the result if we want to apply it for individual people. But it can be done pretty easily using some face scanner apps, even on cell phones. We have tested this automated processing pipeline for animating the expressions and head poses on an improved version of the physics-based neck head face system developed by Lee and Tzaplis. but it can potentially be applied on any muscle-driven model. As for the future work, first of all, we want to add more muscles to activate the facial action units for a higher anatomical accuracy. It's because right now the model still cannot simulate the deformation of some part of the face very well, such as the cheek. And we also would like to extend the system to explicitly control the lips and the eyes, because those are the parts we think has the biggest mismatch from the real human images, as you can see in the picture here. See, the eyes still not match very well. And we would like to experiment the framework on the transfer of mixture of expressions, subtle expressions, and micro expressions, because those are what we perform in daily life, and they often convey some important emotional meaning. Lastly, we want to apply our framework to some other more realistic muscle-driven models. And we think this idea of using an abstraction of muscle actions to achieve a high-level control of coupled muscle activations might be applicable on the biomechanical simulation of other body parts as well. So definitely, we think this would be an interesting direction to explore more. Okay, I think that's, so here are some references we used in our talk. And that's all we want to cover today. Thank you so much for listening. We would like to take any questions. Thanks.
Thank you.
Okay, thank you so much. Thank you, Xiao and Surya, for this very detailed presentation. Any questions from the audience? Or would you like to start some of the common questions that you get, Xiao and Surya, and fill us in?
Sure, yeah. Yeah, I can start with one question. So yeah, I think it's a pretty interesting one. I was asked about, so there were some people asking if we can kind of combine this model with some like a language model to produce some kind of talking face, like for example, like the Toy Jensen model shown in the NVIDIA GTC. And the answer is yes, I think it has this kind of potential. But right now, as I mentioned, one drawback is that we don't have the explicit control of the lips yet. So that kind of like stop us from applying it to integrate it with some language model. But once we have like a very good control for the lips, so it can mimic the talking motion of the human, then I think we can integrate with it with some like state-of-the-art language model to build this kind of talking face that can perform some expressions or motions as the model taught.
Well, that's good. What are some of the applications of this model?
Yeah, so currently, because this model, it emphasizes a lot on the anatomical details. So right now, we think a big application would be in the medical field. Because I know like in the entertainment field, lots of people are still using the like a FACS-based blend shape because it's just faster. So right now, I think this is more for like medical and education usage. But in the future, we would also want to improve this so that it can run like more, so it can be applied in the entertainment industry as well.
That's interesting.
Yeah. Sarah, do you have anything to add?
So, of course, the medical field and the education field are very important, but maybe it is, of course, nowhere near, but these kinds of systems can also be used for some kind of animation in the entertainment industry too. Of course, the capacity to run this real time is not up to mark yet, but maybe if the anatomical model as a whole can be processed very quickly in real time, then this may also find some applications in the entertainment industry in terms of animation, games, etc.
Yeah. I think another potential usage would be robotics, because this kind of system, it emphasizes on like it's dynamic system, so and it has this kind of synthetic muscles, which maybe can potentially be used in robotics as well.
Russell has a question here.
Sure. Yeah. So our we have a company and we're using a lot of CGI to replace expensive film sets in production, and CGI seems to suffer from the uncanny valley in movies. People don't want to watch it. So do you think this or deep fakes or other models in the next 5 years will be improved enough that you can replace Hollywood filming with CGI like this?
Yeah, I think that's a very interesting question. Yeah, I definitely think, as Sarah mentioned, as the like hardware, and also as if we can like further improve like some structure of this model, I think it's definitely applicable in the entertainment industry. I'm not so sure about the I think the uncanny valley, and to my understanding, it may be influenced more by like how we kind of model the human mesh and the texture, right? So if we definitely want to improve this part for our model so that we can kind of cooperate, like incorporate make it more personalized, so we have a personalized look for the model. So I think this has the potential to tackle this problem, uncanny problem.
Cool, thank you.
Welcome.
Can I ask about in the opposite direction, kind of doing non-human type avatars for driving those or in CGI? Is that easy to kind of convert over to that domain?
Sarah, please.
That might be a bit difficult because for non-human, so we are talking about muscle-driven models here. So for non-human avatars, it might be a bit tricky to define some kind of muscles for it. For example, human muscles are very well defined. Like there is a lot of data about how human muscle works, where they are positioned, how much their elasticity is, and a lot of other details. But for these non-human avatars, for example, let's say you want to animate a dragon. Dragon's muscles are not very well defined or well. The data about that does not exist. So this approach might be a little tricky for non-human avatars. If it's a very simple non-human avatar for which muscles can be defined easily, then of course this approach can work very well for that.
I agree. I mean, we think it has a potential to be applied on any muscle-driven model. But it kind of depends on like how accurate the muscle data is. If it's a well-defined muscle, like a well-defined structure for the muscles and the bones, then I think it should work well. Yeah.
Anything else? Any other questions? I was also thinking, Xiao or Surya, how could this be integrated with some language so it can produce, like, let's say, a talking face, like some actions going on?
Yeah, so I think for like a talking face, the most important thing would be the lips movement. I'm not very familiar with language model, so I'm not sure how to sync the lip movement with the language it's speaking. But I'm pretty sure there are lots of like state-of-art research that are tackling this problem. Yeah, but I think once we know the deformation of the lips based on the language it's speaking, then we can and also we need to has the explicit control for the lips in our model. Then we can kind of like combine or integrate this to to having it to making it speak. To making this deform as it speaks. Yeah.
Oh, cool. Interesting. Anything else?
I had a question about symmetry in facial expressions. Do you utilize that at all to speed training, or does that kind of fall out naturally from the neural nets? And the other part is asymmetry, like dealing with a wink or something. Is there a way to kind of deal with both of those aspects? Perhaps just weighting the difference between the two sides.
So yeah, I can take this question. So as for symmetry, I do not program the neural network to know that the expressions need to be symmetric. So the neural network naturally learns. The neural network naturally learns symmetry. So the muscle activations which I produce to get the action unit intensities for the training data have encoded symmetry in them, and the neural network learns to produce symmetry expressions from that. So right now, the muscle activation set which I produced to generate the training data is slightly limited, but I'm sure if we add in asymmetry to that, the neural network will capture those patterns too. So it's definitely possible to learn asymmetry and symmetry both at the same time. And as for your question, could you please repeat your question? I remember it had a different part which I did not address.
Well, I was just bringing up an asymmetric thing as a wink, for instance, just one way. So that was the.
So for the wink, right now we do not have explicit control of the eyes, but assuming we have that particular control, then a wink would definitely be possible, given that we produce some muscle activations given we produce some relevant muscle activations to generate the training data in that way. So if the neural network has seen a wink in the training data, then it's definitely possible to reproduce a human producing a wink or any asymmetric expression for that matter.
Thank you.
Any other questions? Or feel free to write it in the chat if you can't unmute yourselves. Or other than that, we've got 2 more minutes, or we can also start wrapping this up.
I had a question. Was the RAVDS data set? What is that again? The RAVDSS?
Yeah. So it's, if I'm not wrong, it's the Ryerson audio visual data set of song and speech. It's a long name. So
this one.
So in this particular data set, there are multiple human subjects enacting, there are multiple human subjects reciting a song or speaking a sentence in different expressions. So for example, that particular sentence is spoken in a joyful manner, in a surprised manner, in a sad manner, and so on. And that particular song, the one particular song is also sung in different expressions, in a joyful expression, in a disgusted expression, in an angry expression, etc. And they also have 2 levels of intensity. So this is the normal intensity. That means the human actor is singing a song in a sad expression at normal intensity. They also have elevated intensity or high intensity in which the expression is really bold. So that would outline the RAVDS or RAVDESS data set.
Okay, yeah, speaking of singing a song, a couple years ago, we had a speaker talk about doing lip syncing, that it would generate facial or the lips correctly for music.
Yeah.
Oh yeah.
You can see the lips are deform our thinking to some extent. But yeah, but I think but we think it can be further improved.
Yeah, that's good to know. Anything else from the other attendees? Well then, Xiao and Surya, thank you again for your knowledge and for sharing this topic with us. It's been a pleasure. And
thank you so much for the invitation.
Of course.
Yeah, sure, anytime. Also, feel free to check out our meetup for future events.
Mhm.
Okay. Good night,
Yes,
everyone.
sure.
Thank you very much again. Thank you.
Thank you.
Thank you.